Hello, let's do a quick guide of the equation booklet that will be in the exam with you. The equation booklet contains a lot of useful information. And the last section of the equation sheet is ultrasound, and we start with a definition of acoustic impedance, capital Z, and we would literally say the equation here, the product of the density of the material and the speed of sound through that material. The next equation is designed for us to work out how much of the ultrasound is reflected off a boundary or transmitted through a boundary effectively as well. So I'd like to take a little arrow from there down here to give me some drawing space. So this could be a boundary between two materials. We could have Z1, Z2. We would draw the normal, almost look like a ray diagram. We would have some ultrasound coming into the boundary. We would say that that would be the initial intensity of the ultrasound. Some of the ultrasound will be reflecting off that boundary, so that's going to be I subscript little r, but then some of that sound will also be transmitting beyond that boundary. We'd call that intensity transmitted, I subscript t. And we're not really interested in any of the angles here. This isn't like an approximation of Snell's law at all. But it is important to note that accompanying this equation is, if you take the original signal, the intensity of the original signal, it gets split into two parts, a part of it that is reflected and a part of it that transmits beyond the boundary. And sometimes, just keep an eye out, the question in the exam might be calculate how much of the ultrasound is reflected, in which case fine, you can just rearrange this equation. But sometimes it might be how much of it is transmitted through this boundary, in which case you're going to have to do a little secondary calculation in order to find out how much is transmitted by subtracting how much is reflected from the original intensity. The next equation is the Doppler effect, but it's the medical imaging edition. We have a 2 here because the ultrasound is reflected off the moving object. So for example, if a train was making its own whistle, we wouldn't have the 2. If we were whistling and it was reflecting off the train, we need the 2. The cos theta part is because we might not be observing the moving object in the direction that it's moving, and this would allow us to include any odd angles of observation. So for example, if we were observing a moving object at 90 degrees to its velocity, cos of 90 is 0, we wouldn't experience any Doppler effect at all. V is the velocity of the object, and C is not the speed of light, it is the speed of sound through the material the object is travelling through. For example, if we were doing a whistle in a train, C would be the speed of sound in air, about 340 meters per second. Over here we have F. This F, I like to put an F subscript 0 to say that that is the original frequency of the sound that you would hear if it wasn't being Doppler shifted. And then the delta F is the change in frequency because of the Doppler effect. So if it was moving towards you, the frequency that you would detect would be the original frequency plus the change in frequency. But if it was moving away, you would hear the original frequency minus the change in frequency due to the Doppler effect. So police sirens sound higher pitched than normal, a higher frequency than normal when they're moving towards you, and police sirens sound a lower pitch than normal, a lower frequency than normal when they're moving away from you. Good luck in the exam.